properties of molecular solids, and I'm going to be trying to relate this to their their bonding all the way through. So molecular solids are those substances that are made up of molecules. So that's the key. So every molecular solid has molecules at their heart. So oxygen gas, nitrogen gas, carbon dioxide, and water are examples. So the fundamental particle of molecular solids are their molecules. Molecules, of course, are made up of two or more nonmetals, elements that are bonded together or held together by covalent bonds. These covalent bonds, as you should recall, are those electrostatic attractions between the nuclei of one atom and the electrons of an adjacent atom, and vice versa. Covalent bonds tend to be a pretty strong force that hold the atoms together in these molecules, and they lead to a couple of really important physical properties. So here we have oxygen, nitrogen, carbon dioxide, and hydrogen with their Lewis dot diagrams. So you can see the double bonds between the oxygen atoms, the triple bonds between the nitrogen, the two sets of covalent double bonds between carbon and oxygen. So each of these molecules have covalent bonds and pairs of shared electrons, and these tie up the electrons between those atoms. That is, they do what we call localizing the electrons between two nuclei centers. And that's important to remember, because these localized electrons give one of the physical properties, or two of the physical properties actually, to molecular substances that metals, for example, do not have. So the fact that these electrons are localized means that the electrons cannot migrate or move. That's important. So this leads to the fact that one of the major properties of molecular solids is that they are not very good conductors of electricity. They are what we would call insulators. And that's because to be a good conductor of electricity, the substance needs to have either free electrons or delocalized electrons, free moving or free moving ions. Molecular solids just do not have either of those two, because the electrons are tied up in the bonds, and forming ions of the molecules is pretty hard. Now, you should also remember that all substances can exist in any state of matter, whether it be solid, liquid, or gas, and we've talked about this previously. The important thing to remember here is that temperature and pressure are crucial, and by altering the temperature and pressure, this is possible to lower the kinetic energy enough in the molecules to slow them down to allow the intermolecular forces to hold the molecules together. Now, normally with molecular solids, this can't happen because they just have too much kinetic energy, they're moving too fast, and the intermolecular forces just do not have enough chance to operate. So here we have, again, the molecular geometry of each of these molecules, leading to whether they're nonpolar or polar molecules. Nonpolar molecules distribute or demonstrate different physical properties to the polar. And you should review or recap your knowledge of polarity and shapes of molecules if you don't understand these diagrams that are here. So, nonpolar molecules are those which have symmetrical molecular shape, cancelling dipoles, and therefore even electron distribution throughout the molecule, with no overall dipole in the molecule. On the other hand, polar molecules are non-symmetric molecules. They have non-cancelling dipoles, uneven electron distribution, and they have an overall molecular dipole. And it's important to understand here that the electron distribution is at the heart of all of this. So here we have the electron clouds of each of the 4 molecules, and you can see that the nitrogen, oxygen, and carbon dioxide have what we call symmetric molecules with cancelling dipoles or no dipoles at all, and therefore even electron distribution. They are nonpolar. Water, on the other hand, because of its bent shape, bent 4-region shape, will be polar. The forces that hold molecules together are called intermolecular forces, and there are 2 major types of these. And we talked about these on last Friday, London dispersion forces and dipole-dipole, with the extreme case of hydrogen bonding. Non-polar molecules only have London dispersion forces. Polar molecules have both London dispersion and dipole-dipole. So here we have examples of what London dispersion forces are. They're the temporary dipoles created between close molecules, or molecules that are close to each other, and they induce temporary dipoles within each molecule that can then lead to an electrostatic attraction, an instantaneous electrostatic attraction, and this is what we call a London dispersion force. They increase with mass and surface area. On the other hand, dipole-dipole occurs between molecules that have permanent dipoles. So the water molecule here is a polar molecule with permanent dipoles, and they form a stronger than normal attraction between those opposite ends of the polar molecules. This is also important in the solubility of these substances. Hydrogen bonding is just the extreme dipole-dipole and exists only in molecules that have hydrogen and either 1 nitrogen, oxygen, or fluorine. So there's some examples: water, ammonia, and hydrogen fluoride. All molecular substances can have solid structure if the temperature and pressure is such that it lowers the kinetic energy. This concept of lowering kinetic energy sufficiently to allow the forces of attraction to take hold is a really important concept. You must mention this term kinetic energy when you're talking about bonding and physical properties, NCEA, if you want to get the excellence level. The intermolecular forces between molecules are the weakest of all the attractive forces and makes most of the molecular substances either gases or liquids at room temperature. So the melting point and boiling point of molecular solids are very low because a lot of kinetic energy has to be removed from the molecules to allow the intermolecular forces to hold the molecules together. Generally, non-polar molecule substances are gases at room temperature with the lowest melting and boiling points because they only have London dispersion forces, and this means you have to take out an extraordinary amount of energy to even allow the dispersion forces to try and hold the molecules together and preventing them from moving from place to place. So oxygen, nitrogen, they have melting and boiling points down in the -150s to -190 region. Carbon dioxide can be a solid at room temperature, but it sublimes, and water, of course, is a liquid at room temperature. And this leads to generally polar molecules being liquids or solids at room temperature, with melting points being higher than their equivalent size nonpolar molecules, as they have both London dispersion and dipole-dipole attractions, but they're still weak compared to metals, ionic substances, and certainly the giant molecular substances. Hardness is not really a property that you talk about with molecular solids. It's more to do with metals and giant molecular solids. Malleability and Ductility. Well, for obvious reasons, most molecular solids are described as brittle. That is, they shatter easily when a force is applied. And this is because of the weak London dispersion and dipole-dipole forces. They're not malleable, they're not ductile, they couldn't even be considered in those categories. The molecular solids shatter when the force is applied because the intermolecular forces are broken when the molecules move over each other, and this disrupts the bonding patterns. In metals, this does not happen. The bonding pattern is not disrupted, and they are therefore malleable and ductile. But in most others, when you hit them with a hammer, apply a force, they shatter because you disrupt the bonding between the molecules. And in case of ionic substances, you actually put set the same charges above each other. Electrical and thermal conductivity. Well, the electrical conductivity has already been mentioned, but as shown before, they are poor conductors. They're what we would call insulators because they have no free electrons or ion to move under the influence of an electric force field. The electrons are all tied up in the localized electrons of the covalent bond within the molecules. Molecular solids are poor thermal conductors for similar reasons. To be a good thermal conductor, the energy needs to be able to pass, or the vibrational energy of one molecule needs to pass to another one and down the chain for this to happen. However, here, the electrons are not free to do that. In metals, they can, but here, the electrons are just not free to pass the kinetic energy from one molecule to the next. And with even the slightest increase in kinetic energy, the molecules in molecular substance move past so quickly that they too do not have the chance to pass the vibrational kinetic energy on. So they're poor conductors of electricity and conductivity, thermal conductivity. I am going to do a piece on solubility separate. That will be for Friday, and I will relate that back to the experiments for which I put the video on last time. I will make another video to go with this one about some of the special molecular substances that it's useful to know a little bit about.